In my previous video, I showed you how to blink a series of LEDs like these by controlling the individual bits in the I/O port registers to turn the I/O ports on and off and set them high and low to get the LEDs to light like this. And if I let the microcontroller run at full speed, you wouldn't see anything but a blur of LEDs. They'd all appear to be on. And so I used a delay function to give you a bit of time in between each LED so that I could actually see them blinking on and off like this. Now, I used a very wasteful delay function which simply uses up all the resources of the microcontroller for the time that you're delaying for. In this case it was about 500 milliseconds, I believe. And so the microcontroller can't do anything else except service interrupts. And what I'm going to do in this video is show you how to use a timer, one of the 3 timers that are in the ATmega, and show you how to use the timer to generate a regular interrupt, which then you can count to use to give you a specific time delay. And there are 3 timers, as I mentioned, and I'll show you just one, how it works, but all 3 work in a very similar manner. There's some minor differences between the 3 of them. All 3 timers can produce 2 separate PWM outputs, so you get a total of 6 different PWM outputs from the microcontroller. And in a later video I think I'll show you how to program the timers to give you the PWM. But for now, what I'll do is show you how to program the timer, how to program the actual registers that control the timer, and to give you I think I'll pick an arbitrary number of 10 millisecond delay. An interrupt every 10 milliseconds, and then you can count the number of 10 millisecond interrupts to give you something longer. In this case 500 milliseconds, so you would count 50 of those interrupts and it will give you 500 milliseconds. So I'll show you how to do that in the code, but first I think I'm going to give you a description of the registers that are in the timer. Let's get this stuff out of the way here. Now, the core of the timer is a register called the timer counter TCNT0, timer counter 0, because we're going to look at the timer 0 in this case. And they're called timer counters, and a timer is one function and a counter is another function, but the hardware is exactly the same. It's just where the clock pulse comes in, and I'll explain that as we go along here. But the main part of the timer counter is a register, and in this case for timer 0, I'll just go timer counter 0 is what we're going to look at. So the main part of it is a register that's 8 bits long, and it's called TCNT0, timer counter 0, or timer count 0. And there's some logic around it that controls it. Now, it's a special kind of register because it could be manipulated in a couple of different ways. The microcontroller, the CPU in the microcontroller, can actually access this register, and it can write to it and read from it as well. So it can write to it and modify it that way. But it can also be modified with a signal that comes in here, and it's a clock. And what the clock does, there's another one called direction as well. And what the clock does is cause the register to change its value by 1, and depending on the direction signal here. So you can increment the timer counter register by 1 every time it pulses the clock line, or you can decrement it as well. The source of this clock, and this is what determines whether it's a timer or a counter, the source of this clock can come from a couple of different places. It can come from an I/O pin outside the chip, so it can come from a signal outside of the microcontroller, and it can run what they call asynchronously, which means it's not timed with the main timer in the microcontroller. And it can be used for timing irregular events, like what pops to my head right now is something that counts cars going down the street or something like that. So the cars go by randomly, and so it just pulses this counter every time a car goes by, and that's a counter. A timer is something that runs at a regular frequency in here, and this is always incrementing at a constant frequency, and that gives you the timer function. And the signal for that comes from the main processor's main oscillator, FCPU, and in an Arduino that's 16 megahertz. You could run it directly from the FCPU, or you could put it into another device that is called a Prescaler. And so FCPU comes in here, and then the Prescaler has a number of taps coming off of it. And what a Prescaler does is just divides by a certain number. And so these taps could be, I can't remember exactly what they are, but I think it goes from divide by 2 to all the way up to divide by 10 to 1024. So, and then this one might be divide by 2. I have to look it up in the data sheet to figure out what these are, but it's irrelevant at this point. And when you set up the timer counter hardware, you select one of these taps, or you select FCPU directly into the clock, or the external I/O pin. So you have an I/O pin here, and that can go in as well as FCPU. So you have all these different options for incrementing and decrementing the timer counter. Now, as the timer counter is incrementing or decrementing, it's an 8-bit counter, so you'll have 8 bits that start off with all zeros, and they increment, and they can go all the way up till they're all ones. And there's a total of 256 different combinations of ones and zeros with 8 bits. But when it reaches all ones on the next clock pulse, it starts over again at 0, and that's what's called a rollover or an overflow. And there's some logic in around this timer counter register that detects that rollover, and it will set a flag which can be used to set an interrupt. So you can have an interrupt on timer counter overflow, and that's an important interrupt to use. Now, there are 2 more registers that are associated with this clock or this timer counter, and they're important for generating the PWM frequencies. They're called OCR0A and OCR0B, and OC stands for Output Compare Register. So what's going on? There's logic that connects these two registers with the timer counter register, and it's constantly comparing this register with that and this register with that. And when they get a match, you get a signal. You get another flag set, an interrupt flag, and it's called the Output Compare Match flag. So there's a source of 3 different interrupts that you can generate using this timer counter. And what I'm going to do to make the timer work is I'm going to use this register and this register here. I'm going to tell the timer counter register to just keep incrementing, and every time it reaches 0 it's going to start again, and it just keeps incrementing. And then I'm going to put a fixed value into this register, and then these two will get compared, and when this register matches that, or when the timer counter register matches this register, the interrupt will be generated, and this register gets reset to 0. And so it's only going to count from 0 up to the value in this register. And I'll show you why it's important to do it that way, to get the right 10 millisecond delay that I want. Now there's some math in here that we have to perform. So we have a 16 megahertz oscillator, which is the main oscillator in the microcontroller, in the Arduino boards. It could be anything. You could be running your microcontroller with the internal 8 megahertz oscillator, or you could have a different crystal on your setup, whatever you're using. It could be up as high as 20 megahertz. But if we do some math, and at 16 megahertz, if you take 16 megahertz divided by 256, this register here will overflow very quickly, and you'll get an interrupt very quickly, very frequently, and it's faster than the 10 milliseconds that I'm interested in. If you take this 16 megahertz from here, this one is 16 megahertz, and you put it into the Prescaler and you pick one of these taps, you can slow this timer down to a reasonable value. And what I've done when I set it up is I'll choose the 1024 tap here, and so it's going to be going into the clock register here, or the clock line here. And I'll have to sit down and do the math here. In fact, what I'll do is I'll stop for a moment and then I'll do that. So some quick calculations here. 16 megahertz divided by 256, which is the total count in this register, gives me a frequency of 62,500 hertz, which works out to about 16 microseconds for every overflow in here. So we'll get an interrupt every 16 microseconds. So clearly this is way too fast. If we divide this 60 megahertz by 1024, we bring that down to 64 microseconds. Now with 64 microseconds between each pulse here, how many 64 microsecond pulses do I need to get 10 milliseconds? And so what I do is to simply take 10 milliseconds and divide it by 64 microseconds. So 10 milliseconds divided by 64 microseconds gives me a number. And I'll just quickly punch it into my calculator here. 64 and divide. So I get a value of 156.25. So there's a bit of an error there. So I need 156 counts into this register here in order to give me, actually it's 155 counts because you have to take away one for the rollover. But so I put that number here, not the decimal because I can't get it in there, but I put 155 into this register here, like that. And what happens is that this clock will count up from 0 to 155, and when it matches, it creates that interrupt and then resets this register back to 0. So this register doesn't go to as high as 255, which is all ones in there. It only goes up to 155. So it counts from 0 to 155, which is 156 counts. That's where the minus 1 comes from. And so that will give me approximately 10 milliseconds between each interrupt. So that's how we are going to program this timer counter in order to give us a 10 millisecond interrupt. Okay, here we are back in Atmel Studio looking at the code. Now what I did here was I created a new directory or a new project in a new directory, and called it Blink with TC0, and renamed the main file to Blink with TC0.c. And then I went to the old file and I simply copied and pasted it all into here. So this is the original Blink3 file unmodified, and I'll work from here. We'll start modifying things. Now when we're going to use the timer here to create our timing, we're going to unfortunately make the code more complex, because the timing is no longer going to be in line with our code here. We're going to break up our process, which is blinking these LEDs, turning on and off the different LEDs, which is a continuous process, but it's going to get broken up into small chunks now. And what happens here is in between each setting of turning on or off an LED, we can now run something else instead of wasting our time in delay milliseconds in this function here. But in order to do that, we're going to have to remember what state we are in so that we know where to go next when this process here, blinking the LEDs, starts up again. Now this is of course an incredibly simple piece of software here, and it's doing nothing but blinking the LEDs. So I'm just showing you how to break up a process into chunks so that you can do other things. Remember, the microcontroller, there's only one brain in this thing, only one CPU, so it can only do one thing at a time. So it can do a little bit of one thing, put it aside, and then do a little bit of the next thing, put that aside, and go on and do something else. Now in this case there's only going to be the one process, but and then the other process is going to be idle, which is going to do nothing. But this will give you an example of how to break your program up into processes, so that you can have the processor, the CPU, doing things all the time, useful things, instead of wasting time here in a delay function like this. So I think what I'm going to do is, before I start modifying this code to make it work that way, I'm going to go back to the notepad and show you a state diagram, because we're going to have to do this as what's called a state machine, and I'll show you how state machines are made. So we'll have to look at our process of blinking the LEDs as one process, but it's going to be broken up into a number of states. So if we bring the LEDs back in here, so we could make it quite simply a number of states, and each state being one of these LEDs being turned on. So in this case there could be 6 states, and the state machine will just keep track of what state it's in, so it can switch to the next state, which then would turn on a different LED. And then when it gets to this last state, it'll swing back around and then switch on this LED, going back to the first state again. And in between each of these LEDs and this last state would be where you would do something else with the microcontroller for up to 10 milliseconds. So you can look at it this way, as you can draw a state diagram with these little circles. The way I do it anyways is, this is a state, and let's just say this is LED number 1, and then the next state the machine it will be in is LED number 2, and so on and so forth. Now let's put them all in here. That's 3, that's 4, LED number 5, and LED number 6. Number 6. And then the end, it's wrapping around and coming back to the beginning again. So, and the state flows in this direction. We'll put arrows on these guys, like this. Now, this is not a flow of software. This is not flowing from one function to the next. This is not a pseudo code diagram of how the actual software runs. This is a state diagram. So some processes that you might want to do might actually have the same kind of code executing in each one of these states, but it may be working on different variables or something else. And so I just want to get it clear here that this is not a flow of software. This is a flow of state. A little hard perhaps to understand if you haven't done this before, but this is how we do it. And generally how to keep track of what state you're in is you'll have a state counter. So we could call our state counter LED state, and it can count from 0 up to 5. Goes from 0 to 5. So this would be state 0, state 1, state 2, 3, 4, and 5. And what this arrow here means is how did you, what happened to get you from one state to the next. Now there could be a state machine that you stay in one state checking a bit, and so you might draw your little state arrow like this, and you're checking a bit to see if the bit gets set. But as long as the bit is cleared, you would always stay in this state. And then when the bit gets set, so let's just do this here. Bit equals 0 keeps you in this state. Bit equals 1. And then when the bit gets set, boom, you pop over to the next state. So what happens is there would be a bit of code that would increment LED state to the next one, number 1, and then it would sit in this state for however long it's necessary. Now in our case here with this blinking LEDs, what changes the state is the timer. In this case it would be timer counter 0, what do they call it, output compare register 0 A, oops, that was a D, not very good at printing here, interrupt. that's what the state change would be down here. Same with, in fact, it changes this every time there's an interrupt, the state changes. And so I'll show you how to do that in the software with the interrupt, and how to decide what state you're actually in, again with the software, looking at this value here in LED state. So let's go back to Atmel Studio and start putting that kind of software together. So back here in Atmel Studio and looking at the software. So this is really quite clear to, it looks like my state diagram that I just showed you. So this would be state 0, state 1, state 2, etc., etc. But how do we divide these up into different states? And again, we're going to stay inside this while one loop. It's always going to loop forever. And so we've got to look at something in order to keep us out of this part of the code while we're waiting for the interrupt. But first of all, let me show you how to set up something like this, how to determine what state you're in. And we're going to use a C coding statement called the switch statement. And first of all, I'm going to go back here and I'm going to define a variable. It doesn't have to be very big, so we'll make it 8 bits. And we'll call it, as I had on my drawing, LED state. And we don't need to initialize it. It starts at 0. I'll initialize it later. Now, I might want to define, well, we've got the variable. Now we need to know what goes inside that variable. And what I'm going to do is create another, or use another C coding function here, or coding style. Can't think of the right word here. It's called the enum, or enumerate, and it looks like this. And inside here there will be names, variable, or not variable names, we'll call them names. Let's call them LED state 0, and we'll put in 5 of these because there are 5 states. I'm just going to do it by a copy and paste. 2, 3, 4, 5, 0, 1, 2, 3, and 4. No, actually there's 6 states, right? Because there's 6 LEDs. And we'll put in number 5 here. Last one doesn't need a comma. So this just defines, it's like defining constants. I could use a define statement like this and just say define LED state 0 and then space 0 and then 1 and 2 and 3 and 4 and 5, etc. for all of these different numbers. I could do it that way. This saves a bit of typing, but also this is flexible. So if, for example, we needed to change the way our project operated and we had to add a bunch more states, well, I simply just type them into here and I don't have to type in all these different define statements. And also this automatically numbers your states for you, and so this one will be given the value of 0, and this is 1, 2, 3, 4, and 5. What I typically do, because you need to check when you've gone beyond the end of these numbers of states, I put in something I call max LED state, and that's just a number that's the beyond the end of these 6 states, and so I can use it for checking so I don't go too far, because I have to increment this, but the variable that contains these numbers, the LED state here, but when I got to detect when it's reached the end of this so I can start back at 0 again, and this is what I put in here. So this is automatically giving me a bunch of numbers here, 0 through 6. Let's see, how do we do? Let's do our switch statement in here. So it looks like this, switch. And what we're going to switch is we have to switch a variable, and of course it's going to be our LED state variable, and inside curly brackets, and I want to do all of these here, so I will put the curly bracket at the end here, and just for good looks here, I'm going to indent all of this. And it's easy to do that with Atmel Studio. You highlight it and hit the tab key and it indents it. And it needs to go in a bit more than that, so I'll do that. Now, the switch statement by itself is useless, and you have to add something else here. And what you do is you have to put in the cases. So case, and our first state is LED state 0. So LED state 0, followed by a colon, and at the end of, and then what follows this is the code that will execute when LED state equals this variable here. And to know where the end of this code is so it doesn't do anything else, we put in what's called a break statement, like this, with a semicolon after it. So what it means is that when it gets to this code, or it gets to this statement here, it looks at LED state. What value does LED state have in it? And it looks through all these case statements. It finds the value that equals this value here. It executes the code here till it gets to the break statement, and then it drops out to the very end of the switch statement. So what I like to do in my code to help me keep track of my brackets here, so you can see how Atmel Studio highlights the brackets. See that one? This one down here is highlighted a different color, and so these are the two matching brackets. So I know this is the end of the switch statement. So what I'll do is I'll put a comment at the end of the switch statement just to tell me where the end of the switch statement actually is. Oops, right here. So I'll put in a comment. So I'll say end switch LED state, and that just tells me that's the end of the switch statement. Now we're not going to use our delay anymore, so I'll take it out. Now let's look at our next case here. So actually I'm going to just leave a bit of space here, tab it in, case LED state 1, colon. After that we put our break, and so on and so on. So I'm going to shut down the camera here, or the capture, and I'll finish all of this off. There's no point in wasting any time. But I think this is fairly easy to understand. When it reaches the code, when the CPU reaches this statement here, we will look at the value in LED state and look to see which one it is, and it'll actually go directly to the code that's in here. So if it happens to be LED state 1, it won't execute this. It will execute this stuff here, hit the break statement, go to the bottom here to the switch statement, and then goes back to the wait or the while. So let's they'll just finish this off camera. So here we are back to the code with all the case statements put in. While I was doing this, I realized that we needed an extra state, so I added LED state 6, and I added it to here, back to our enum statement. And so you see how this works. LED state is evaluated, and then just the code that relates to whatever LED state is executed, and then it hits the end of the case or the switch statement and goes on and does something else. There's one more thing I didn't talk about, is this default, which means anything else other than the states or 7 states that I've shown here. And what I did in this case is does nothing. Nothing changes. It's just a catch-all. If somehow LED state gets incremented beyond state 6, it's a catch-all in case something like that happens, and it's a good thing. A good thing to put in there. You can actually put some code in here. So what happens if it does run off to the end of this? What can you do here? I can't think of anything to do right now, so it doesn't really matter to put nothing in there. So that is how we break up our code into different states and how we remember what the state is between. We have to now figure out how we're going to increment this and deal with it with our timer. But now let's look at how to set up our timer here. So our I/O ports have been set up here, so the next thing is to look at the timer. Now the timer has let's go to the timer here. It has two control registers. Let's just scroll down here and go directly to the register descriptions. Timer control register 0A, R0 just means 0 just means timer 0. The other two timers have the same names for the register, just that this number here is actually 1 or 2 for the other timers, and all three timers have the same registers here, and I believe essentially the same bits in each register. Now these timer controller or timer counters are quite complicated. They have a lot of features, and so there is a lot of stuff to set up, and I will go into some detail just to do what we have to do right now, and then when I show you how to do a PWM, I'll go into additional detail on how to set up these registers. So there's timer counter register A and then timer counter register B down here. And let's go back up to this one again. Whoops, a little too far. Way too far. Where did I go here? Let's just go back to this. Alright, back to where we are. So we've got two bits here, and these two bits, WGM 1 and 0, well actually let's go back because the order that these are described, it starts at bit 7 and goes backwards. So you've got COM 0A and COM 0B, and there are 2 bits for each of those. And all they do is determine how the output pin of the output compare register, the pin that's associated with the two output compare registers, how they're going to react. In our case here today, we're not going to use them, and so we're just going to leave them in mode 0, which is normal port operation. The output compare register pin is disconnected. And it's the same for both register A and register B. How they react depends on what mode that you have the timer in, and we're going to be in a very simple mode, which is this one down here called, where is it? It must be the first one. Okay, yes, this one's compare output mode, non-PWM mode. So we're not doing PWM. And so we leave them both at 0, and A and B are the same, so we can just put zeros in both of these registers. What these bits down here show you is that these are the reset values, so we don't even have to change most of this register here because of it comes up in the mode that we want when it resets. The WGM 0 and 1 bits here are they determine the clock frequency. Or sorry, they determine the mode of operation of the timer counter. And so there are up to 8 different modes. There's only 2 bits in this register, and there's yet another bit, WGM 0 bit 2 is in this other register. And I'm not sure why they did it this way, because there were 2 bits left over in the timer control register A, and they could have put that in there, and it makes it a bit weird to set it up. So these 2 bits here are in the first timer control register A, and then this bit here is in timer control register B. And so you pick the mode that you want it to operate in, and I want it to operate in this, CTC. And it escapes me at the moment what CTC stands for. But this is the mode that we want. So we need to set WGM 0, 1, and 0, which is in timer control register A, to 1, 0, and then in the remaining bit in register timer control register B to a 0 to get it in the mode that we want. So what this should I explain this now? No, I'm not going to explain this stuff just yet. I'll go into more detail in another video. I want to try to keep this one, the details down in this one, so it's a little easier to understand. So and then we set this bit in here to 0, which is already 0 on reset, so we probably don't have to do anything with that. The next 3 bits here that we're going to work with, these ones we don't care about right now. We're not going to forcing an output compare, so we can ignore those for now, and they're in the state that we want them in, which is 0, so we'll just ignore them. It's these 3 bits that we have to look at next. and there's another table here, and this sets up the clock for the timer counter register. What source is the clock? And if you set them all to 0, there's no clock source, so that means the clock will not be incremented and nothing's going to happen. The timer counter is not going to do anything. You won't be generating any interrupts, it won't be counting, it won't be doing anything. And you can select the different prescalers. So with these 3 bits set this way, there is no prescaling, and the source of the clock is coming from FCPU, which is, in the case of an Arduino, the board that I'm using, is 16 megahertz, and it makes the clock tick pretty quickly. And you have a number of choices here. You can have a divide by 8, divide by 64, 256, or 1024. And as I showed in my paper example earlier, 1024 is the only one that actually works. It slows down the 16 megahertz oscillator to a level that we can generate count within 200, which is less than 255, which is the maximum value of the timer counter register. And then here, these two states here, or these two modes, just determine what the signal on the timer 0 pin. So this is now external clock source from outside the microcontroller on the timer 0 pin. And you can have a clock on the falling edge or the rising edge. We'll talk about that maybe in another video, because this you can use as an external frequency counter, or the source for a frequency counter, which I've done a previous video on that, and I might do again another one here with more details to show you how to set it up. So that is the 2 control registers, how we set them up. So we're going to put 101 into the lower 3 bits of timer control register B. And then this goes on and describes the other register. This is the counter register. This is the register that gets incremented by the clock. We can write to this and we can read from it, but today we're not going to do anything with it. I don't really care what the value is in here. It's just going to automatically get incremented all on its own by our clock source here, which would be FCPU divided by 1024. These are the 2 output compare registers, A and B. We're going to work with register A, and we put in the value into this register, what the timer counter will count up to, and then it will trigger the interrupt, and then this register here, timer counter, will get reset to 0 and it'll start all over again. So it'll count continuously between 0 and whatever value we put into here, given that we've selected this mode here of CTC. Compare timer. Actually, it's probably described here. Anyways, I can't remember what CTC actually stands for. It doesn't matter. This is the mode that we want, and that's what we'll program into those two registers. So let's go back to the software, and what we're going to do is timer counter control register 0A equals, and I can't remember, I haven't written this down, so I'm going to go back and have a look again what we're going to do. And we need to, do we need to do anything to this? Actually, oh yeah, we had reset value of those two are 0, 0, and we are in mode, scroll down here, hopefully this program will, so it's 1, 0, so we have to write 1, 0 in the upper 2 bits, and then nothing else, everything else is 0. So we can just write to it directly. We don't have to do this bit manipulation like we did here. Equals 0B, meaning I'm going to write a binary number here. So all the first 6, 2, 3, 4, 5, 6 bits are 0, and a 1, 0. And then we're going to write into timer counter control register 0B. And I'll do it the same way, since we only have to do this with once. We don't need to worry about the other bits. We'll go back to this. Now we know that this bit has to be set to 0, so we don't have to do anything with it. And we're going to select this here. So the upper 3 or the lower 3 bits will be 1, 0, 1, and those are the only bits that we need to change. We'll go back to that. So 5, 1, 2, 3, 4, 5. The last 3 bits are going to look like this. And so there we go. I manually figured out which bits to set and clear, but it's pretty simple. There are other ways of doing this in a similar manner to this. I have a file, a driver file that I can use to set up the timer control or timer counter registers, or for timer counter 0. I have a bunch of software that I've already written, and I can include it in here, and I can set these up with a little more less cryptic. Having just a bunch of ones and zeros here doesn't mean anything to you when you look at it, but when you have actual words in here instead, it does mean something, and you get a better idea of how it works. And I can show you how I've done that later. But for now, we're setting up our timer counter so that it will run continuously. It'll count up at that speed, 16 megahertz divided by 1024, and it'll count up to a certain value. Now, what's that value? So we're going to set our output compare register 0A to a value. Now, I can sit down and do the mathematics. In fact, I did that already with my paper earlier, and I came up with a number of, what did I get? 155 is what should be put in here. So we can just go 155, and there we go. Again, I don't like to do this kind of thing because it's kind of cryptic, and where did 155 come from? So we can put a comment here and say it's F CPU divided by 1024, and then we're going to divide it by how many 10 millisecond interrupt is how many times per second. Well, it's 100 times per second, and we have to take away 1 because it counts, the number is too big. By that, it's the incorrect value, and 1 is brings it closer to the correct value. So I could do that too. I could actually have written that directly in there instead of the 155 and let the compiler figure it out. And that, in fact, I find that I would do this more often, do it this method more often than this method, because this actually means something. I can make this value here. I can change this value if I want to change the my timer interrupt time. For say I want it to be every millisecond, so I would put 1000 in here. But I can make this a defined value and write it up somewhere here, and I could just have one place in here that changes this value and gives me different timing. But this will work. Now the last thing we got to set up is the interrupts, the interrupt register. So timer counter interrupt mask register, and these are the 3 bits that are affected. When on reset, they're 0, so it means none of these interrupts are enabled. And I want to set this one here, output compare interrupt enable A, and that's the bit 1. So let's go back to our code. What was the name of that? TMSK0. TMSK0. Oh, TIM. There we go. Equals, and I'll just do it again, 0B, and 1, 2, 3, 4, 5, 6, 1, 0. So now I've enabled the interrupt. So that's how to set up the timer counter to do what we're doing here. I encourage you to, on your own time, if you want to learn how to do this, get the data sheet. You can get it from Atmel. It's a free download, and read through it. So now I'm going to create an interrupt service routine in order to do something with this timer counter.